as you might have noticed, so I'm coming from the French part of Switzerland. I'm going to talk about cryptography, more exactly about the real security of open source general purpose cryptographic library that everybody is using. And I'm going to focus on their security on embedded platforms. So first of all, I will talk a bit about cryptography and security at large. Then I'm going to focus on side channel attacks, which is a kind of, let's say, unexpected type of attacks which appeared about 15 years ago in the context of cryptography. And finally, we'll have a look at cryptographic libraries like OpenSSL and many others. So let's begin by with the cryptography. So with the apparition of internet, but although many other networks like GSM, we can say that the use of cryptography has exploded, and thanks to this guy here, who is Bruce Schneier, who wrote a very famous book called Applied Cryptography. Everybody was able to use cryptography. So this book detailed how programmers and electronic communication professionals can use cryptography, the technique of enciphering and deciphering messages to maintain and to guarantee the privacy of computer data. So long so far. Everybody is in the book. Developers just have to read the book, maybe grab the source code which was included in the book, and everybody will be fine and have secure system. Of course, it's not the case. If we take the list of 25 most threatened bugs of this, which is published and maintained by the Science Institute, we see that in the error category porous defenses, at least 4 categories are related to cryptography. So for instance, still 15 years after the book of Bruce Schneier, people forget to encrypt sensitive data. People still use hard-coded passwords and hard-coded secrets like secret keys in their software. They still forget to authenticate critical function. And finally, they still use broken or risky cryptographic algorithms. So it looks like that cryptography might not be that easy to implement in a proper way. So now I'm going to ask myself what might go wrong when using cryptography. So one of the first examples is just a bad choice of primitive cryptography. Let's take, for instance, the case of the Xbox. The story tells that the developers of the Xbox security function, so the developers of the secure boot algorithm, had to find a teeny encryption algorithm because they don't have much room to implement it. So they just went to Google. This is more than Google in 2010, maybe it did not look like that. And they asked for a teeny encryption algorithm, and fortunately, they found a teeny encryption algorithm. More exactly, the teeny encryption algorithm, which is a precise block cipher. And what they did is that they used this block cipher as a compression function to build a hash function. This homebrew hash function was then used to hash all the boot sequence and all the code in order to authenticate it and to ensure that had not been modified, for instance, for hacking it. Unfortunately, if you go to Wikipedia tells us that in '96 we already knew that T suffers from equivalent keys, meaning keys with different values but which encrypt every plaintext to the same, which implement the same permutation. And basically, when you consider equivalent keys in hash mode, this is equal to collisions. So it means that the hash function was badly broken. Another very famous example is the use of RC4 in the wireless, the wireless standard, security standard. Unfortunately, once RC4 suffers from several statistical imperfections in the, let's say, 256 first output bytes, and those statistical imperfections allow just to break it very, very easily, as everybody knows it here, using tools like aircrack. So that's another example of bad choice of a stream cipher. We could also speak about the MD5 hash function, which has been severely broken in 2004 by a Chinese researcher. MD5 is still one of the most widely deployed hash function, and researchers begin to be able to play and have funny application of this collision, for instance, generating certificates for different identities, but with the same signature and so on. So this is another bad choice, another example of bad choice of primitive. But now you could also imagine doing other stuff wrong using cryptography. You could imagine to choose in a bad way the protocol. Let's take, for instance, the case of IPsec. So IPsec allows to set up several different security configurations. Experts now would say too much different security configurations. But basically, you can say, I'm just going to encrypt my data. You can say, I'm just going to authenticate my data. Or I'm going to encrypt and authenticate at the same time. The first possibility here is also a very bad choice. Already the title of this paper suggests this, attacking the IPsec standards in encryption-only configuration. So if you encrypt only and you forget to authenticate, there you're going to suffer. And they say the new attacks are both efficient and realistic. They are ciphertext only, so you only need to know a bit of ciphertext, and only the capability to eavesdrop an ESP encrypted traffic and to inject traffic into the network. So this is an example of bad choice of protocols, bad choice of configuration, which is still present today in a very famous security standard like IPsec. Another example about what might go wrong is just, as everybody knows, the bad choice of key size. For instance, if you look at the TLS standard, you still have a lot of security suites which are completely insecure, which have, for instance, export compliant key sizes, which is 40 bits for security ciphers and 512 bits for 512 bits for asymmetric ciphers like RSA. And if you don't care about this key size, maybe you are going to have your application at risk when using cryptography, although you are using cryptography to secure everything. And this example of machine, which is a Copacabana device, which can be bought for in the order of 10,000 euros, is able to break a 56 key, a less key in average in 4 or 5 days. So it just costs you 10,000 euros to break cryptography with key lengths which are much, much too small. Another example, funny example of last year, it's the RSA key used by a Texas Instrument to secure the boot process of its calculator. And basically they used 512-bit RSA modulus. And in 2009, so at the end of the summer or during the summer, ever mysterious Benjamin Moody posted a crypted message on the United TI forum yesterday, and he said that he factorized this 512 modulus. So let's go and have a look at this cryptic message. The community have been politely asked to remove the former content of this post, so you might expect that some lawyers went there, but basically it's not a problem because the guy just engraved on his calculator case the values of the prime numbers. But more seriously, this was one of the very first examples of having somebody not being an expert in factorization in cryptography, just grabbing some open source factorization software out of the internet, filling it with 512 modulus and waiting for 73 days on a single PC and having at the end the RSA key completely broken. So please choose in a way sufficiently large key size in your application. Now, there is plenty of other examples of bad use of cryptography. For instance, the famous LAN manager hash by Microsoft, who screwed completely the authentication scheme. Philip might say a bit more about this later, or not. There are plenty of ways to use incorrectly RSA. If you just think about encrypting a symmetrical key of even an AES key of 128 bit with a small public exponent like E = 3, then you're gonna have some fun. You can imagine sign with RSA without any message processing, and then you are gonna suffer also. So they really have many other ways to do cryptography wrong. And of course, the list of errors is still not complete. This is just a very small example. Fortunately, correctly designed and properly analyzed primitives do exist. Let's take a few examples. If you have to choose a block cipher, then if you choose AES, you are most likely going to be on the safe side. If you have to choose a hash function, we know that the SHA-2 hash function family is resisting all the attempts of cryptanalyzing, and there is a high likelihood that you will stay on the safe side as well. If you are playing with RSA and choose good standards like OIP for encryption and PSS for signature, then you don't take much risk because those primitives have been very well analyzed. You can do key agreement protocol using elliptic curves and Diffie-Hellman. You can choose a whole security protocol like TLS 1.2, and you are gonna to have a proper cryptography. So, good. My question now is the following. Has the Lambda developer needing crypto any chance to stand on the safe side without doing any mistake? And the answer is, well, that's a bit more complicated than this. Let's talk a bit about side channel attacks. So, first of all, I have to define what are adversaries in a cryptography world. Let's first consider black box adversaries. And this is the usual definition of an adversary, of an enemy for theoretical cryptographers. Basically, it's a nice guy, like this. Because, why he's a nice guy? Because he's gonna to fit within a security model. So in that case, it's possible to model my algorithm, my protocol, my system as a set of so-called oracles, and I'm going to interact with those hidden objects, for instance, using a ciphertext on the attack, a non-plaintext ciphertext, or maybe even chosen plaintext ciphertext answer, and then I'm going to be able to say clever things about my algorithm. I will even be able to prove mathematically in a certain way that my algorithm is secure if the underlying cryptographic primitives are secure. And this is a typical example of RSA OIP for RSA encryption and RSA PSS for signature, where we are able to say if it is difficult to factorize, then my signal nature scheme will be strong. If it is difficult to factorize, then my encryption scheme will be solid. There is always this if, but this is another story. And then there are gray box adversaries. So that is a type of adversaries that were not foreseen by the theoretical cryptographer, let's say 20 years ago. Basically, they can interact with the cryptographic primitives, but they might have just a little bit more information about the computations. Like for instance, the timings which are used to compute an operation involving secret keys, or maybe some physical information about physical leakage, like power consumption, or maybe they are just able to perturb the computation and to induce faults in the computations. And girls are pretty good at, for instance, at exploiting side-channel information, or poker player know side-channel information at the tail, for instance. And basically, those are very, very powerful adversaries. And there is even worse, there is the white box adversaries. so the real bad guys. And those are adversaries that most cryptographers just do not want to hear about because it's render their job completely impossible. So they can just do everything they want. They can completely reverse engineer all the software, the hardware they would like. They can read, write all memories, including the secure ones, including the memories containing keys, for instance. They can perturb all computations every time as they like. This is typically a real adversary that we might find in the field and which are breaking cryptographic systems today. And it's very, very difficult to thwart them. So this talk is focusing also on embedded platforms. So what is an embedded platform? So typically it's a teeny, small, very small computer like a smart card, maybe a USB dongle, a Victorinox ultra secure flash memory, or maybe even a kind of cheap PC like a game console, for instance. All of these are embedded platforms. I will just put them in the same vein. Basically, the main characteristics of embedded platforms for an adversary, for an attacker, is that they are not remote, they are local, so you can have them in hand. So it's not a remote server somewhere on the internet. They use rather slow clocks. They are quite cheap, so you can buy several of them if you would like to analyze them. And this is something to keep in mind. So now I'm going to focus on side channel attacks. I will just speak about timing attacks, physical attacks, and attacks based on faults. But let's have a first look at timing attacks. So timing attacks have been discovered or maybe rediscovered by Paul Kocher in the middle of the 90s. And he presented a paper in a cryptographic conference implementing timing attacks against diffie-Hellman, RSA, and other number-theoretic-based ciphers. And he said that by carefully measuring the amount of time required to perform private key operation, so operation involving some secret, attackers may be able to find fixed diffie-Hellman exponents, factor RSA keys, and break other crypto systems. And basically, those kind of attacks are extremely powerful and very, very efficient. So it's not theoretical attacks involving billions of quantum computers. It's just an attack that can be performed using a single computer and maybe a bit of electronic devices or something like that. And he showed at that time that a typical RSA implementation, which was RSA Ref, so the reference implementation sold by RSA Laboratories at that time, was completely dependent on the data and on the value of the private key. So, okay. We can find timing attacks also in other cryptographic components. Let's take, for instance, the CBC encryption mode, which allows to encrypt large data set using a small block cipher. And everybody knows about the CBC mode. And basically, there is a small issue with the CBC mode. It requires a small practical issue. It requires that the data which you would like to encrypt have a length which is a multiple of the underlying block cipher block size. So it has to be a multiple of 16 bytes if you are going to use AES, for instance, or a multiple of 8 bytes if you are using triple S. But CBC encryption doesn't tell how to encrypt, for instance, 3 bytes, or maybe 13 bytes, or maybe, I don't know, 2 to the 10 plus 1 bytes. So for this, we have to pad, basically, so to add a few bytes. And one of the standard padding with 8-byte blocks is the following. If 3 bytes are missing, then you are going to pad with 3 octets with the value 3. If 7 bytes are missing, you are going to pad with 7 octets with the 7 value. And if you have already a multiple of 8 or let's say 16 bytes, then you are just going to add a further block padded with 8 times the value 8 in case of 8-byte blocks. And the problem is that if the padding checking routine is not time constant, So let me translate it in another way. If the padding checking routine is time optimized to be as quick as possible, then you are in trouble. And this was illustrated by a paper written by Swiss researchers now 7 years ago, where they were able to see that they were able to intercept password encrypted using IMAP password, encrypted using the SSL TLS protocol implemented by the OpenSSL toolkit, and to recover it on a local LAN quite easy. Those padding oracles have been revisited recently, and there was an attack presented on the ASP.NET framework this year, where the guys were not using timing differences, but they were just using the fact that the ASP.NET framework gave 2 different error messages in case of a padding problem or any other problem. And it is possible then to decrypt, to transform your ASP.NET framework in a decryption oracle, which is quite true. Another timing attacks is the example of cache attacks, where you are also going to exploit different timings of, for instance, of an AS implementation, where you are going to exploit the fact that data, so the AS implementation will do table lookups which depend on the secret key value, and those table lookups will take some time or not, depending on whether the data are in the L1 cache or maybe they are not in the cache but in the RAM. And typically you have penalties of several hundred clock cycles, several dozens of clock cycles if your data are in the RAM instead of being in the L1 cache. And if you have a concurrent process which just try to trash the cache lines and to observe whether the data looked up by the AES process was in the cache or in the RAM, then you can recover very easily an AES key. And this was a nightmare, at least for 3 weeks for the Intel people, because they believed that their CPU was unable to do proper AES encryption. We have also other examples of attacks, side channel attacks. Let's have a look at physical leakage. As a matter of fact, computation executed on any kind of platform, being software, hardware, FPGA, or I don't know what, it will consume energy. And basically, if it is possible to measure this energy, which is possible in an embedded system, and if this energy consumption is dependent on secret value, then those secrets are not secure anymore. And we can imagine at least 2 examples of physical leakage, like a typical power consumption leakage, where we have a setup here with a scope and a single PC. But this could also be electromagnetic emanations, where since every electronic device will just emanate electromagnetic variations, and the intensity of this variation could be different depending on the secret value. And this paper, also by the same Paul Kocher, 2 years after the timing attack, shook completely the silicon industry, because he saw that he demonstrated that most smart cards, which was considered as being real safe for secrets like secret key and secret RSA key, were completely vulnerable to these power consumption attacks. And it was very easy to recover those secrets out of a smart card. And the idea is just the following. You are going to modelize the transition of data in a register by saying, okay, if at a clock cycle, at a precise clock cycle time, you have no transition in your register, then it will consume a bit of energy. But if you have to flip all the bits in your register, then it's going to consume more energy. And just depending on this knowledge, then you can attack ciphers like AES and TDES in a very efficient way. But there is even worse. There are fault attacks. So just have a look at the following piece of code that could validate, for instance, the RSA signature during a secure boot mechanism of a trusted device. So somewhere we could have following line. So if RSA verify of the signature is okay, then we are going to continue the boot process. Otherwise, we are maybe just finish the boot process and go out with an error. So if you go to the assembly level, maybe this will translate into the following. You will have something like a compare value with a 0 or 1 case of success or not. And then you will have a jump depending on this value. So basically, you can have the largest RSA key size. The whole RSA signature verification mechanism security will rely on whether this jump instruction will be executed or not. Okay. So you are just, if you are able to make this jump instruction to transform it in a jump always, or just to vanish it using some magic tricks, then the whole secure boot process will fail. And this has been proposed about 20 years ago, also against smart card processors by people from the University of Cambridge. And they show that if you take a smart card and you introduce small power glitches, then you can just make some instruction erase. And typically you can erase instructions implementing security check or secure boot checks or all this kind of stuff. So those glitch attacks are extremely powerful. You can also induce faults using, for instance, a laser on a smart card. And the two devices there come from the pay TV hacker world and are called unloopers. And they are small glitches, so small secrets which are able to introduce small spikes of current into a secret, and thus to make it fault. So now, what about OpenSSL and sisters? So we know today several general purpose open source cryptographic libraries. For instance, OpenSSL is the most well known, but we have libgcrypt, Mozilla NSS, LibTomCrypt, and many others, and it is by far not an exhaustive list. And the question I'd like to partially answer right now is, how secure are those general purpose open source cryptographic libraries? And of course, secure, I mean in the context of resistance to well-known cryptographic attacks, but also in the context of the resistance to side channel attacks. Okay? We could also imagine measure their security, for instance, with respect of best practices in terms of secure programming, or the reactivity of its developers when confronted to security issue. I'm going to focus on these 2 points. And for this, I choose an attack which was invented by James Monger, Crypto01, and this attack. So it's a kind of mathematical attack, but a side channel attack. It attacks bad implementation of the RSA OAP padding mechanism. And it was very funny because at this conference, it was a crypto conference, in the same session, you had a paper showing that the proof of security of RSA OAP was broken. You had a paper repairing the broken proof, and at the same time, so saying that RSA OAP is secure. And at the same time, you had a third paper, which was a paper by James Monger, which says, we don't care about security proof. Basically, if you have a bad implementation of this, then I can break it in milliseconds. And so this attack transforms a bad implementation, so typically a time-dependent implementation, into a decryption oracle. So you have a server, maybe, or a smart card implementing a decryption operation. You don't know the secret key used to decrypt this stuff, and you can submit ciphertext. And basically, if the ciphertext decrypts properly, then it will return you the plaintext. But you never see this case. But you are going to submit special ciphertext and to observe the reaction to errors. So basically, you will just to ask about, let's say, 1,000 questions to your oracle to decrypt 1024-bit RSA ciphertext, which is very, very efficient. And the only required information that you need is, does the decrypted ciphertext have the most significant byte equal to 0? That's the only thing you need to know. You don't need to know anything about the plaintext. And if you are able to make a difference when the decrypted ciphertext has a 0 in its most significant byte or something else, if you can exploit this difference, then you will transform this in a decryption operator. So this is the whole padding mechanism, which is pretty complicated. So it involves hash function and secret random values and all this kind of stuff, just to, for instance, to recover this. And at the very beginning, you have a 0 byte. And this is what you are gonna to attach. Okay? Just this 0 byte. So we can obtain this information using a body permutation of RSA, at least through error messages. 7 years ago, you had different error messages in most libraries saying it's a problem of padding, or maybe it's something else. But you can also exploit it using timing differences. And now I'm going to focus on the OpenSSL implementation. And if you look at the changes file, then you see that this routine, so this attack has been, of course, known by the OpenSSL developers, and that they are going to, they had improved the RSA padding, check OAP, check to avoid the reach attack using huge encoding parameters and so on and so on. Note that the RSA OAP padding routine does not use encoding parameters and hence one's not vulnerable. Okay, fine. Let's have a further look. If you're gonna to have a look at the source code, in the source code, then you say you can read signaling this error immediately after detection might allow for side channel attacks. Look at the paper of James Manger and etc. etc. So we are using a bad flag. But have a look a bit even further, and what you see is that you see a test. Wow, that's fine. You have a test which says in that case. So here it's computed as a different length of big numbers, but if this test is taken, then we are in the case where we don't would like to disclose the fact that it's not a 0 byte. We are just putting a flag bad which will be propagated later until the end of the decoding routine, and you close this test. But you have a test, and yeah, unfortunately, the CPU's instruction pointers, branch predictor, are not designed to keep information secret. What you have to know is that a typical Intel CPU has a branch prediction mechanism, which for each branch will try to guess where it is, and if it makes a wrong guess, then you will have hundreds of cycles of penalty, typically to resynchronize caches and all this kind of stuff. So. Is that time constant? Okay, let's try. I'm going to have a round number here of checks on my MacBook. And you will see that just for 1 million checks, if you look at the difference of timing, you already have like something like, which looks like to be quite significant. So it's more than a tenth of a second. And you might say, okay, but come on, you had some luck, and it's not significant in the statistical way. So let's have a look at 1,000 independent measures of this of checks. But here I'm just going to take 10 times less check at a time, just because I was in a hurry to finish my size. And what you see is that you really see a time difference. So only the fact that there is a few instructions which are embedded in the if case, it means that this routine check is broken with respect to Manger attack. So, do I have now to say that OpenSSL is broken? Let's take the case of high-end servers, remote servers, and desktop computers. Well, in theory, yes. Now, in practice, the number of samples you have to measure in order to remove the noise, maybe due to network latency and to the noise introduced by the OS and switching tasks, and is probably too large. Probably, I don't know. maybe we can try it, but it will require millions or maybe billions of measurements. So in that case, you can say, okay, OpenSSL is quite well protected against malware attack. But if you put OpenSSL within an embedded platform, within a smart card, if you like, if you steal this source code to put it in a smart card or in a USB device or any embedded processor, then I would say, yes, it is definitely broken. Why? Because on those kind of platforms, you can do clock cycle accurate measurements. If your CPU is working at 20 megahertz or maybe 50 megahertz, even 100 megahertz, then you can do clock cycle accurate measurement and you will see the difference. And even if it is time constant, but the execution of the instruction, so the flow of instruction is not the same, then you can use a power trace to see the difference between the two behaviors. Okay, now just have a bit of analysis of all these kind of cryptographic libraries, and I'm going to have the following legend. So we'll just have a look at classical timing attacks, cache attacks, oracle attacks, so padding oracle attacks, the physical leakage attacks, and attacks based on faults. And I'm just going to give 3 different grades. So some serious care has been taken to thwart these attacks, some care but not always, or not properly has been taken, or there were no care at all behind these attacks. And what we see is that, yeah, it's not that good. So let's take OpenSSL. So OpenSSL is just the most widely deployed open source general purpose crypto library. So it's present in every, it's used in every SSH daemon, in every Apache installation. So basically, OpenSSL is everywhere, and it has an excellent reputation. So we see that they have taken some care again, timing attacks. So for instance, they are using blinding, random blinding for protecting the RSA implementation against timing attacks. They have done some work against cache attacks, against oracle attacks, but they did not take all the care which is required, as I demonstrated later. But there is no protection against leakage attack and no protection at all against fault attacks. If you have a look at libgcrypt, which is written by the developers of the GNU-PG application, which is a typical crypto tool, then you see that they only care about timing attacks on the RSA, and no care at all is taken on the other type of attacks. Let's take another nasty case, LibTomCrypt. So LibTomCrypt was written by an enthusiastic teenager, which was crazy. So he was 17 years old at that time, which was crazy about cryptography. And basically, he was a good programmer, and he wrote quite optimized crypto routines in his LibTomCrypt library. And furthermore, this library is very convenient because it has a completely free license. It's not even GPL. So everybody can just steal his source code and put it in every possible application. But the problem is the focus was on speed. And when you focus on speed, you forget to focus on security. So basically, there is no protection at all in any single lines of its source code. Let's have a look at Mozilla NSS, which is the cryptolib using the implementation of Firefox, for instance, or Thunderbird, and all this kind of such software. So here you see it's interesting. Timing attacks are protected. They do not mention at all anything about cache attacks. Oracle attacks are protected against a bit like OpenSSL, so there is a bit of difference, but not that more. Nothing about leakage attack, but they introduce some protection against some types of fault attack. I don't know why. That's fun. NaCl. NaCl, it's a library written by cryptographers during a European project. And one of its features was to have a high-speed implementation. So it should ring a bell, but also know that data-dependent branches. So some cares have been taken to do a proper implementation. Unfortunately, and very unfortunately, only a very small set of completely exotic cryptographic primitives is supported. These exotic primitives are completely secure. They are very high security primitives, but you cannot use them in any standard products because you don't have the standard algorithm. And no care is taken about timing attacks, full care against cache attacks and oracle attacks, but no care about leakage and faults and U-turn. Botan, written in C++, which I learned to know about 3 days ago. This is interesting because you have full protection against cache attacks and timing attacks, a new time about oracle attacks, and a bit against fault attacks. So you see that the developer is quite aware of this kind of stuff. But you have interesting comments in the source code. So you have a big tree of ifs and tests and else, which is typically not time constant. And the question, is it vulnerable to timing attacks? The answer is, of course, it is vulnerable. So, and even more on embedded platforms. Crypto++, written by Weidai, which to a library which has been present by now for a long time in the field. It is even conform to FIPS 140-2 level 1, blah, 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 blah. So this library has been certified. A new time, you see that the only correct protection is implemented regarding timing attacks, and there is minimal protection against cache attacks and oracle attacks, and nothing about leakage. Just an example. This is how OAP is implemented. A new time you have tests, and you have not only one test, but you have one test, two tests, and three tests. That's bad. And your compiler is not going to save you here. Cryptlib, written by Peter Gutmann, which is a well-known security expert. So this library is quite good because also maybe because of some pressure of the market, because he sells his library. So it's open source, it's free for free applications, but it sells it to everyone which is willing to buy it. And in that case, we see that it's quite well protected against timing attacks, not at all against cache attacks. Maybe he just skipped the paper, but there is a bit of protection against oracle attacks, leakage attacks, which is one of the only one, and fault attacks as well. So, for instance, he implements CRC checks on the values of private keys which are stored in memory, so that you cannot disturb them. So it's quite a good result. So I think it's time to conclude. This is the high-level view of what we have of open source crypto library, and what we see is that this high-level view is quite bad in my opinion, because if you were to use any of these libraries on an embedded platform for some security critical mission, then you really are going to have troubles. But what we can see that the best libraries we know still know a certain level of protection against all these kind of attacks, even if those level of protection are most of the time not complete. And basically it's not that because it is difficult to write a time constant, even a flow constant cryptographic implementation of a cryptographic algorithm. It just requires time. So it's possible to do it, but it requires time. And it has not been done so far. So my conclusion will be the following. Also, we have good general purpose crypto libraries. They are not quite badly protected against timing attacks, leakage attacks, and fault attacks. Basically, these observations, so don't interpret my talk in a wrong way. So those observations have not an extreme impact on their security when they are used for what they were designed to be used, meaning production servers or even desktop computers. What I would like to emphasize here is that if you are going to use this on embedded platforms, then this is going to be very, very risky. And basically, an efficient and properly secure open source crypto library are still to be written, in my opinion. And that's everything I wanted to say today. Thank you very much. So I don't know whether there are questions.
Yeah, I've got a question.
Yep.
Have you had a look at all at any like proper commercial crypto libraries, like those provided by PGP or Entrust?
No.
No.
Not yet.
Did you plan to look at that?
I have no idea about those commercial stuff. I also would like to have a look at the crypto API of Microsoft, but some reverse engineering work is to be performed. But I don't know. I guess that some similar findings will be fine. Yep.
Don't you think that the cache effects and cache attacks could be avoided at compiler level somehow?
That's, for instance, what is done in OpenSSL. For instance, they try to prefetch data when they're going to use those table lookups or those table depending on the secret key, and they are prefetching everything. But another possibility is to use smaller tables, and which completely fits into the cache and this kind of stuff. But still, this will. I'm not sure this will completely protect against this kind of attacks, because all the time it's just a matter of noise added to the measurements and the number of samples you can take. So even with the greatest noise within the signal, you can filter it if you have enough samples. It's just it's just math there. Basically, I would say that implementing an AES or triple S using table lookups will never, so you will never be able to completely protect against this kind of attacks. But it's not a problem, because we know how to implement AES today in a constant way. And we know at least two possibilities, so using completely standard instructions, or and having still a reasonable speed, or in the very latest Intel CPUs, you even have AES accelerating instructions, which are completely time constant, and you don't suffer from this problem. So I would say just forget about table lookups approaches, and better focus on either the dedicated instructions or the time constant implementation. Yep.
What are the timing attacks applicable to knuckle?
It's just that they are not using a blinding when they are doing an exponentiation or let's say a multiplication or analytic curves. They don't use any blinding, and depending on a random value. That's a bit surprising. I was a bit surprised. So it means that basically you can just use the very old attack of Paul Koch against this time, and download. Any other questions?
Is there any chance that on the new processors we might find errors like this in the instructions that do the crypto, and then you can't patch anymore? Because you just said something like, well, if you do it with a dedicated instruction on your processor, then it's going to be perfect. But couldn't they do the same errors, and then we would have a hardware problem?
For instance, regarding AES, well, now there is literature that such an error. I would be, so they will really have to try hard to make this error, I would say. Because it's completely computing on the fly. Those stuff are not using memory and pre-computed tables, but are just hardwired and computed using Boolean gates. So no, I don't think this should be a problem. Okay. So I'm finished. Thank you very much.
Thank you very much.